All right, so this is very, very similar to number 4 on the quiz. The only thing I changed is on the quiz, I think it's got a 4 right there, and I put a 9 right there. Very, very simple. All right, what are we going to do? And why do you want x to be 3 secant theta? Very good. All right, so what I always have to do is I always have to write down these identities. So sine squared plus cosine squared equals 1. Dividing by cosine squared, that means tangent squared plus 1 equals secant squared. All right, and then what I have to do is I have to look at this. I want something squared minus 9. So looking at this one, I can take secant squared minus 1 and get tangent squared. So I always have to write down those identities to figure out which substitution I'm going to do. Some people simply memorize, if it's in this form, I always use secant. You have to do it one way or the other. Either memorize the forms or derive them from the formulas. It's always secant, tangent, or sine. And I know when I need the sine one. If this was 9 minus x squared, I know that one's the sine, just because I've done that one so many times. That's the most common one. All right, so I think you're exactly right. I think we want x to be 3 secant theta, which makes dx 3 secant theta tangent theta, d theta. And then, you're absolutely right, what's going to happen with the square root thing? Square root of x squared minus 9 is going to become square root of 9 secant squared theta minus 9. You factor the 9 out, and you're left with secant squared minus 1, which is tangent squared. So the whole square root thing simplifies down to be 3 tangent theta. And that's the whole idea behind trig substitution. The whole idea behind trig substitution is to make those square roots disappear.
So whenever you have a trig substitution problem, do you put that as sine squared x plus cosine squared x will eventually get to what you need?
Yes. All right, so now we substitute. This integral becomes dx. dx we decided was 3 secant theta tangent theta, d theta. X squared is going to be 9 secant squared theta. And the square root turned out to be 3 tangent theta. So some good stuff happens. What's the good stuff that happens? Things cancel. Tangent reduces with tangent. 3 reduces with 3. Secant reduces with secant. So I'm left with 1/9 integral cosine, right? Because it's 1 over secant. 1 over secant is the only thing left. There's a secant left on bottom, but 1 over secant is cosine. And I like that because I know the integral of cosine. The integral of cosine is sine. Negative? Positive sign? Positive? So that's 1/9 sine theta plus c. All right, and then I got to get my x's back in. So I take this. I think of x over 3 equals secant theta. I draw myself a triangle. There's theta. It's a right triangle. What does secant have on top? Secant is who over what? Hypotenuse over adjacent. Pythagoras tells me the other side is square root of x squared minus 9. And again, it always cycles back to that. That square root was the problem to begin with. That's always going to happen on this triangle. So, final answer is 1/9. The sign is going to be opposite over hypotenuse. So that's square root of x squared minus 9 over x plus c. Questions on that one?
I just have the other number 3. There's a race to the 3 halves.
Uh-huh.
So what do you do different? Like, really change your answer that much?
Not that much. Let me grab one out of the book here that has a 3/2 power. About 1 over x squared plus 25 to the 3/2. So different problem, but you'll see what happens with the 3/2. Looking back at my trig identities, what's my substitution this time? Not sine. Tangent, because I want tangent squared plus 1. Tangent squared plus 1. So it's not just tangent, x should be 5 tangent. X should be 5 tangent theta. Dx will then be 5 secant squared theta d theta. All right, and let's see what's going to happen with this thing here. X squared plus 25 to the 3/2 will be 25 tangent squared theta plus 25 all to the 3/2. I factor the 25 out, and I'm left with tangent squared plus 1. But I'm not going to write tangent squared plus 1. I'm going to write secant squared all to the 3/2. All right, so how much is 25 to the 3/2? You're way too big. What's the 3/2 power? What's the 2 on bottom tell you to do? Square root. So what's the square root of 25? And then the 3 on top tells you to cube it. What's 5 cubed? 125. Same thing happens here. We have secant squared, but the 2 on bottom tells me square root it. What happens when I take secant squared and I do a square root? I get secant, but then the 3 on top tells me cube it. So that's secant cubed. So that's all that 3/2 power does. You can think of that 3/2 power as being a square root. It's a square root and then a cube. So the same idea, the whole idea behind trig substitution is to make that square root go away. All right, well, we might as well finish this. We've done all the hard work now. So we're going to have integral 1 over 125 secant cubed. And then on top, our dx became 5 secant squared. And that's going to work out very, very nicely again. Reduce the 5 with the 125. You've got a 25 on bottom. Reduce the secant squared with the secant cubed, and you're left with a secant on bottom, which is a cosine. So again, our powers of trig for these last two problems have worked out very nicely. We get very, very easy integrals. We don't have to do some of our tricks for powers of trig. All right, so we have 1/25 sine theta plus c. And then finally, I need to do the same trick. I have tangent of theta is x over 5 from this equation up here. Draw my triangle. Opposite over adjacent. Square root of x squared plus 25. Final answer looks like 1/25 x divided by square root of x squared plus 25 plus c. Questions on that? Yes.
Other questions?
Sure.
Related to the test. Are we going to have to know a bunch of the hyperbolic identities?
For the test coming up?
Yeah.
No, we've already had a test on the hyperbolic.
Right. But, I mean, I knew we were using a lot of the identities here, so I wasn't sure if we were going to try to, if there was any way that was hyperbolic.
Did have some that eventually after negative should fit into a hyperbolic inverse.
Well, but I'm thinking
Yeah.
more like if we have, like, not these substitutions, but where we have, like, the powers of trig, we had, like, powers of hyperbolic trig on the test.
No, you won't have powers of hyperbolic trig on the test. Absolutely not.
Is that going to be, like, next Friday?
Nope.
No?
Oh, the test, you mean?
Yeah.
I thought you meant powers of hyperbolic
No.
trig. The test. Well, let's see. That's a good question. Today we will do. Where are we here? 8.6. We did 8.5 already. So today we'll do 8.6. And then I would say 8.7 will take us at least one day, maybe two. 8.8, probably one day on 8.8. It's after 8.8. Test number 3. Or 9.1, depending on how we want to do things. I would say
We have the test before the break.
we're going to have the test before the break, definitely, because we've got this week and next week before the break.
There's no point in going on break and coming back and being like, hey, let's come back into it.
So I would say in theory we could get the test in on Friday, but I'd be reluctant to do that.
This Friday?
Yeah.
I see what you mean.
I'd be reluctant to do that because it means we would cover material on Wednesday and then that material would be on the test on Friday. I don't like to do that in general. I like to have at least one day for you to ask questions.
How long did Tuesday work last?
Tuesday, next week,
How long did it work for
worked fine for me. That'll work for everybody else. So I think we're looking at Tuesday next week would be when we have our exam. Other questions?
Is there going to be a competency in this one?
This one does have a competency. All these integration techniques.
Isn't that just the whole exam?
Except for the last 3 sections, yes. Yes, it is.
It's pretty much everything.
So pretty much almost this whole exam is a competency. That's correct.
Why'd you have to bring that up?
It's going to be there. Yeah.
Now we're never completely impressed.
Other questions? All right. So back to section 8.6. Section 8.6 is called integration by tables. No, this will not be part of the competency.
So where do you like stop? Integration by trig?
8.2 through 8.5. 8.2 started with powers of trig, and then we had, 8.2 was integration by parts. So there was parts, powers of trig, trig substitution, and partial fractions. So those are your competencies.
So is this class going to take an hour?
It'll take like an hour and 20 minutes at most.
2 problems?
There'll be more than 2.
I don't know, some of those probably have the best time for 2 minutes in class.
Yeah, they're good time, good
This
time.
is like 4 hours, so.
All right, you're going to like section 8.6. Here's what's going to happen in section 8.6. I'm going to give you a problem. What you're going to do is you're going to look at the problem. And then you're going to flip to the back of this book. And you're going to look at these integration tables. And you're going to try to make the problem I just gave you fit one of these integration forms.
Oh, okay.
There you go. So you're going to pick from one of those formulas.
I don't know how much that and trigonometrics.
Now, here's the interesting thing. Well, maybe not interesting. This is an abbreviated list of all the potential integration forms. There are, I should have brought it today. I have a book in my office.
Spend 15 minutes just looking for the integral you want to.
Correct. So your book has 99 options.
There's 100.
Huh? Oh, there's 100. There's 100 over
I
there.
found number.
Your book has 100 options, but there are a lot more than those in real life. If I remember, I'll try to bring my CRC book tomorrow that has a table of integrations in it. All right, so let's see how this is going to work. Let's pick one of these problems here. How about, I don't want to lose that page. I don't want to find it again. The integral of 4x over 2 minus 5x squared dx. Well, yeah, this section, this problem I'm picking is out of page 555, and it's appendix A3 in the back. It says A3 at the bottom there. All right, so we have 4x over 2 minus 5x squared. If I weren't looking in the table, how could I answer that problem? I don't think that's a trig substitution problem. Trig substitutions usually have square roots, not squares. I don't think it's a trig sub.
Try multiplying it out quick.
Partial fractions would definitely work. You would have a over 2 minus 5x, and then b over 2 minus 5x squared. Partial fractions would be one way you could do this problem. Anybody got another way? Foiling at the bottom and dividing is not going to help. You divide when the power on top is bigger than the power on bottom. I don't think that's going to help.
What about following out the bottom and completing the square?
Yeah, that's what I was wondering.
Well, if you FOIL at the bottom and complete the square, you're going to get 2 minus 5x squared.
You could FOIL it out. Well, you know, this one is factorable.
Yeah.
All right, the other way that I can think of to do it is to let u equal 2 minus 5x. And then that x on top, you would say x is u minus 2 over negative 5. So you could do it that technique that you used in Calc 1, the double substitution sort of thing, I think would work also. All right, but that's not what we're going to do. We're going to look for a pattern in our book that looks just like that problem. Anybody see one? Oh, I can't make it bigger.
It's not.
3, 4, 5?
Read the number
Because
five.
yeah, jump.
I think it's number 4. Because we have an x on top. Our problem had an x on top, right?
Pull the 4 out.
Right, we can pull that 4 out. That number that was in front of the x, we can just pull out. A plus bx on bottom. So I think we could write this way. This is 4, the integral of x over 2 plus negative 5x squared. So having a minus there really isn't a big problem. I read it as plus and negative. So I think we want to use integration table number 4, where we have u over a plus bu. And in this case, a is the number 2, and b is the number...
What's the power on number 5?
The power on negative 5 is an n.
That's the same thing as 4 then? Or
No. So this one specifically only has a square. So if you had like a 5th power, if this were a 5th power right
no?
here,
So that would work with 2 then?
this one would also work with 2. Yes, it would.
It would just work out.
But it would work out to give you the same answer as number 4.
Oh, okay.
So yes, this one would work with n equals 2.
Cubed or higher.
But yeah, typically you'd use that with cubed or higher.
That doesn't say it can't be 1 or 2?
No, it does say it can't be 1 or 2.
Well, 2 minus 2 is 0.
But the good news is we have one for power 1, we have one for power 2,
And then everything else.
and then we have one for everything else. All right, so it looks like our answer is, we got the 4 there. 1 over b squared, that's going to be 1 over 25. A over a plus bu, so that's 2 over 2 minus 5x, plus ln a plus bu, 2 minus 5x, plus c. That's it. There's our answer. Pretty easy.
How did they come up with this? They just go through and
This-
over 100 different ways to solve these things. And why give us formulas for them? Because there's so many. There's no point in teaching them kids because you spend an entire year on just trying to teach them all these different techniques.
Yeah, I think that's a big part of it. Although most of these, like if you look at a lot of these, I think you could let x equal a plus bu and do that double substitution trick, and I think you could get almost all of these to work. 10, 11, 12, and 13, those are all partial fractions problems.
It's just for convenience.
It's really just for convenience. 14 and 15 are complete the square and then use formulas that we already have.
That
17
17 is interesting.
is a weird one, isn't it? If A is positive, you get an ln thing. If A is negative, you get an arctan thing. That's interesting.
So how is this going to be on the test?
How is this going to be on the test? Reality is it isn't. No, I do not expect you to put this entire table on your index card.
It'd be pretty impressive. Put specifically number 3, 49, and 51 up.
Right. So this is just to give you an idea of how integrals are really done in real life. Most of the time, for most integrals, people in general aren't going to sit down and integrate by parts. They're going to pull out a reference book somewhere and they're going to see, can I match my formula to one that's already
An
known?
hour going through and trying to find out what that actually matches to all the, how many, just roughly how many of them
I don't know. Like I say, I have a reference book in my office. I'll try to remember to bring it tomorrow.
Is this what a computer program uses essentially? Like they listen to the, like these formats.
are? Like, you mean like Wolfram and...
Yeah, I'm sure they work on like complicated systems, but
That's an excellent question. I do not know.
It'd probably be better to have it coded to actually do the math than to have it try to match something, but it'd be easier to code it.
Yeah.
well, with Lila science, like how it knows that we have like an equivalent answer, like the computer probably has something like that, right?
No. What I'd be more willing to bet WebAssign does to check equivalent answers, I'd be willing to bet it probably plugs in a couple values and just tests them. That would be my guess. I think that would be the most efficient way. So it might tell you sometimes that they are equivalent, when they really aren't, just because they might have plugged in the right numbers where they match.
How many numbers did you do? Did you
It wouldn't take that's my,
compute points? Just
yeah. I would doubt it does that many. I would think 3 or 4 would be enough to
that's
pretty well convince you that they're equal. But I don't know for sure. I have no idea how computers are programmed to evaluate integrals. I don't know how Wolfram Alpha does it. That would be an interesting question. All right, let's pick another one here. Anybody see one that looks like fun?
Oh, it's 27.
27 looks like a good time. All right. So 27 has the integral of cosine theta over 3 plus 2 sine theta plus sine squared theta d theta. All right, so we flip to the back. Then we start looking for a formula that matches. Well, I'm going to start with forms involving sines and cosines. That's, I think, a good place to start. Look for division 1.
Those all have ones in the top.
And,
So then you manipulate it to get one on the top of bars?
oh, I don't know. Must be on the next page. Nope. Nope. No, you picked the right one. So this brings up a point. Sometimes before you can find one that fits, before you can use the tables, sometimes you have to do a U substitution. So what's the obvious U substitution for this problem? U should be sine because du would be cosine. So sometimes these will not fit easily into the table until you do a U substitution. So this becomes 1, so you wanted a 1 on top, 3 plus 2u plus u squared du.
Now we don't even have to look at the trig function.
Correct. Now this really isn't a trig function problem at all. Sneaky. All right, so now we're looking for a plus bu plus u squared, it looks like to me. Let's see if we can find one that looks like. How about 1 over a plus bu plus cu squared? That's number 14. And in our case, c is the number 1. And we get 2 different potential answers depending on if b squared is less than 4ac or if b squared is greater than 4ac. So in this case, let's see, b squared would be 2, squared is 4. 4 would be less than 4 times 1 times 3, 4ac. All right, so we're in the case where b squared is less than 4ac. So we have this answer.
How do they figure that out? This square,
Is the
Oh, I got a good answer for that one. You should know the answer to this one. Tell me about b squared and 4ac.
Oh,
It's under the
b squared minus 4ac.
b squared minus 4ac is part of the quadratic formula, right? So what's happening if b squared is less than 4ac?
You get negative imaginary.
You're getting a negative and you're getting imaginary answers.
You don't like that.
We don't like that, but it forces one thing to happen. Conversely, if the determinant, that's not determinant, it's called the discriminant. If the discriminant is positive, you get something else. And so basically what's happening is, if the discriminant is positive, when you this bottom's going to factor, and you can use partial fractions. If this discriminant is negative, the bottom will not factor. You have to complete the square, when you complete the square, you get the arctan form. So that's the difference in the two. All right, so it's quite a mess, but here's our answer. Looking at the table. 2 over. You can't see the butt, can you? There it is. 2 over the square root of 4ac. 4ac in this case is 12 minus b squared, that's 4, times the arctan of 2cu. C was 1, so that's 2u plus b was 2, divided by the square root of 4 times 3 is 12 minus 4 plus c. That makes the final answer. 2 divided by the square root of 8 arctan of 2 sine theta plus 2 over square root of 8 plus c. Questions on that one? All right, so the only thing that is new in this section that I would quiz you on, test you on, is this right here. If you have rational functions involving sines and cosines, here's the u substitution you're going to make. U is sine x over 1 plus cosine x, which happens to be the same as tangent of x over 2. And when that happens, cosine x is 1 minus u squared over 1 plus u squared. Sine of x is 2u over 1 plus u squared. And dx is 2 du over 1 plus u squared. You need to see some examples. That needs to go on your note card. That's on page 554. It's going to be a very crowded note card. All right, so it's going to look like these problems. The integral of 1 over 2 minus 3 sine theta d theta. Okay, so that's what they mean when they say a rational function involving sines and cosines. Rational function means fraction. And in this case, sines and cosines, we only have sines. All right, so we're going to go back. And we're going to let u equal that. And it turns out that one's really not important. What's important is sine becomes that one. So I'm going to put that in for sine. And dx becomes that one.
So we don't do like use or
You just plug it right in.
Sine of x equals 2u over 1 plus u squared.
Sine of x is 2u over 1 plus u squared. That's correct. What's u going to be in this case? U is tangent of x over 2. And in this case, we're not using x, we're using theta. So this could be 1 over 2 minus 3 sine x dx. We're using theta instead of x, that's all. All right, so instead of sine theta, for sine theta, we're going to write 2u over 1 plus u squared. And for d theta, we're going to write 2 du over 1 plus u squared. So for this problem, there's our two substitutions. There's no cosine for this problem, so we don't need to substitute for the cosine. Let's see what happens. We get the integral of 1 over 2 minus 3 times 2u over 1 plus u squared times 2 over 1 plus u squared du. So it made all the sines and cosines go away. Now what? Cancel? What do you mean by cancel?
Well, you've got,
Well, if you're almost right. I'm going to take this 1 plus u squared, and I'm going to distribute it through, so the 1 plus u squared is going to cancel with that one. But I got to distribute, I'm going to take the 1 plus u squared and multiply it by the 2 also.
first, you can pull a 2 out.
That 2?
No, on the bottom, there's 2 minus 3 times 2 over whatever, but the 2 can be pulled out. The 2 can't.
Okay.
So you have 1 plus 3 u over 1 plus u squared, right?
All right, so I could factor a 2 out, and then even better, once I factor the 2 out, I could cancel it with that one, couldn't I?
Yeah.
All right, so let's do that. See what's happening here? All right, so I'm gonna factor these 2's right here. I'm gonna factor those out, and then I can reduce it with that one. So these become 1's.
So we have 1 plus u squared minus u.
So we have 1 on top, and then I agree. We have 1 plus u squared minus 3u on bottom. All right, so I'm just going to rewrite things. That's integral 1 over u squared minus 3u plus 1 du. Well, I think that's our only choice, actually, is completing the square. Because I was really hoping, what happens quite often is this thing will factor. And if it can factor, then what do? You can use partial fractions. In this case, I don't think this one factors. So I think our only choice is complete the square. So I got to take that negative 3 halves and square it. So that's 9/4. So there's my magic number to add and subtract. So this is 1 over u squared minus 3u plus 9/4 minus 9/4 plus 1. Okay. So that's u minus 3 halves squared minus 5/4. And then that's supposed to match something we know.
That would be the reverse side tension. Like u squared minus a squared.
I think u squared plus a squared is inverse tangent. I think it's one of the hyperbolic ones.
I was hoping it wasn't one of the. No, I was like, please, just let it be.
So we could find one of those numbers.
I suppose it's possible. Well, let's see. This one has a squared minus u squared. That's not quite it.
U squared minus a.
I have u squared minus a squared. I can fix that. How do I fix that? Multiply top and bottom by -1. So that becomes integral -1 over 5/4 minus u minus 3 halves squared. Yeah, put the negative out front. So it looks like our final answer is we're going to have -1. There you go. 1 over 2a. So that's 1 over, what's a?
Square root of 5 and 4.
Square root of 5 fourths.
It's 2a.
1 over 2a. ln of a plus u, so a is square root of 5 fourths plus u minus 3 halves over square root of 5 fourths minus u plus 3 halves plus c. Could.
You get that 2 in the square root of 4.
Yeah, the 2 would reduce with the square root of 4.
And then we get just negative 1 over the square root of 5.
Doesn't really change a whole lot. And then we're still not done.
We got to plug in u, so we kind of.
We got to get rid of the u's and get back to our original problem had thetas in it.
So u equal tangent of x.
So u was tangent of theta over 2. So my final answer would be, I ran out of room on my paper here. Wherever I have a u, I'm not going to write u anymore. I'm going to write tangent of theta over 2. So somebody said, so couldn't these inverse hyperbolic things show up on the test? The answer is I will make sure I pick problems where these inverse hyperbolic things do not end up on the test. You will not have to have that on your note card for this test.
I do have a question though. Will this stuff we just did on page 5/1, will that be on the competency of the test?
That I don't remember. I have to go back and look and see what's on the competency. I
You said
haven't.
it was just 8.2.
Yeah, I might have lied.
You may have been mistaken.
I may have been mistaken. I don't remember. I have to go back and look and see what the competency covers. I don't remember right off the top of my head. Other questions? All right, so this should be one of the easier sections. For the most part, you're just matching integrals to this big table in the back here, wherever it went.
3a.
There it is.
So I hope we're up to date on library skills.
Questions on anything?